So, welcome everyone. This is an excellent, beautiful day for work. If you look out, you see the beautiful weather, which helps us to keep inside the room and do the right stuff for today. So, I'm Gergely Vanaföldi. I'm leading the Wigner Scientific Computing Laboratory. And as many of you know very well, that we used to have 2 events per year. One is the GPU Day, where people who are joining us using our computers, having projects and so on, present their results. And the other is a kind of lecture, which is attached together with a hands-on session. And this is the Lectures on Modern Computing Sciences series. Before we jump to the main stuff, which is a quite interesting topic, that how to use large language models in science. Of course, I mean, most of you have used already the ChatGPT and other things, but this is the way how you can turn it to your scientific direction. Let me introduce the Wigner Scientific Computing Laboratory. So the role of the laboratory is mainly, okay, so we formed the group like 40 years ago, and the main aim was to develop the parallel computing, later quantum computing, and also artificial intelligence. So this massive parallel HPC technologies for science. So the main point from our side is we have a couple of experts. We have, I wouldn't say I am expert, but we have a couple of experts in our group. And we have also a wide, broad interest and knowledge about how other people work around the world. So we can bring it to you and you can learn how to use the things. And of course, you can also join the laboratory with your projects, whatever it is, and then you can learn more about it. So this was the aim how we formed this. And then we got more and more deep. Today we have 3 members and we are open to hire one new one. So Gábor Bíró is a former student of mine. Today is a postdoc. Balázs Kacskovics. Balázs is just doing something. He is just finishing PhD student, and myself. So just in picture the rows. So as you see, to compute something develops from the very early stages, like abacus style, and then it's getting more and more. I think the size is shrinking in some sense, but the users are always there and they need help. And this is the point where we are coming to the picture. So we are the ones who try to connect you to the newest technologies and so on. The short history. So we started the Wigner Scientific Computing Laboratory. Original name was the Wigner GPU Laboratory. At that time, the GPUs was only used mostly for gaming and having nice pictures and so on. But there was a movement that to use these boosted technologies, boosted calculations in science, and that was the point when we jumped on the train and tried to form this GPU laboratory. So in 2005 to 2008 was the early stages. Then in 2009 we made a decision and we formed the Wigner GPU laboratory. And since then we have regular meetings, which used to be the GPU Day first, but later it split it to the 2 events, one for the hands-on session and the other is the project presentation. And we started with Daniel Berényi and Nagy Egrimate. They are both now in the market and doing big money. But this was the time, so in 2010, GPU Day series started, and this was the point of splitting in 2016. And the next milestone was the 2021 when we got this National Research Institute infrastructure title from. Yeah, here is the point. During COVID, I had to move to page to receive this excellent certificate. Okay, so the hardware is what we have just to be in the big picture. So the Wigner Analysis Facility, this is a dedicated site for the CERN ALICE experiment. It's about 5,000 cores and about 1.5 petabyte disk, which is used by ALICE. We have also the Wigner GPU laboratories with many different machines. We have an 800, 8x800 super computer module, and this you can use for specific things. For example, this is the one we will use today for some of our exercises. And also we have the WRHC Tier 2 grid site, which is serving the ALICE and CMS general needs. This is a compulsory part for the CERN ALICE and CMS experiment. I'm actually coming from the high energy physics area. Okay, so here you see the different parts, and this is actually the room 2, where we have the racks. Here you see and how we occupy this. So some of the computers is pretty dense, so you really have to put it to different assets. So the events, what you see that here I collected a couple of posters of the earlier events, and this is the previous GPU day, which we had in June, and also the lectures on modern computing science, scientific computing and programming series. We have also GitHub and the YouTube channel. So most of the earlier presentations are available on the YouTube. Some of them has been nicely cutted, and you can really go step by step. Some of them just in junk. And today we also made a record. So please take into account. I think I forgot to put this GDPR stuff, but if you ask any question, this will be recorded. So do good questions. Okay, the projects. So here you see that what is the statistics for the GPU days. We have not statistics from the very early ages, but typically we used to have like 100 people coming from the industry, coming from academia, and many of the young colleagues. We have so far, this is the 10th of the model lectures in the series. We have more than 55 fellowship programs. Already we have 35 plus industrial and academic partners, and 70 plus scientific publications and program course, which is related to us. Here you see the attendance of the lectures in modern computing in science series also. So we are fluctuating around 40, 50, some years are higher. This year we are about 40. Some people will come later, some people will join online. Let's see. There are a lot of projects. You can read about it. Just scanning the QR code, you can see the finished projects and the list of publications from our website, which is also available. Just a few beautiful pictures. So we are very much connected to the CERN ALICE experiment, gravitational waves, which is responsible by Balázs work. Here you see the same thing what Interstellar did. In the movie, they said that it was a very big major development from the Hollywood community to reproduce this, and this was done by one of our students in 2 days. So that's about science. This is a very high resolution, very high time resolution modeling of the Paks nuclear plant inner site, which was done also on our machines. We have our project, the Hygiene++ parallel Monte Carlo generator development, and this is one of my favorites. Is the song of song of a bird living in a Carpathian basin, and we analyze this via AI technologies, that how he tried to attack the females. Okay, so of course we are contributed to the society. So this is how we have during COVID time. We got some certificates because very large work units has been used by finding the way on solving the pandemic problems. And the future is the today and tomorrow, and this is the event for today, so the lectures on modern computing in science. And I want to also advertise this academic interesting matching event called IML 24, which is promoted from the high energy physics, this is HIP community, to join together people. This event is free for you. You can still register. This will be in the Hotel Mercure Uda Castle Hill, near to the Vérmező place. And this is 2-day, 1.5 day events, and you can still go online and find and come to visit us. There is a registration fee, but it's not applied for you. So you are all welcome to join. This is tomorrow and day after tomorrow, so Thursday, Friday. Okay, we have, I mean, the future in general in your hands, so you can join us with your projects. You should write just a one-page proposal, tell that how much needs do you have, what kind of computational problem you have. You can find everything in this, and even in some cases, if we are lucky, we are over for this year, that maybe next year we can have some budget, so we can also support young scientists with the projects. The only requirement is to produce a paper in 3 months. Which is, I think it's a very good business and deal. Okay, you can find everything in wfclab.wigner.hu and you see earlier projects over the web page. Yeah, and the other things about the future. So we are doing, of course, I haven't changed the title, but of course next year we will have the GPU days, and fortunately also the lectures and we hope some further hardware developments, and we are very much connected with the Euro HPC and the Levante project, which nobody knows whether we will have it or not, but we are on the track. At least you see the partners we have so far during the years, and here you see more on the VSC Lab. You can go online and find my lectures here, and I think this is all what I just wanted to say as an introduction. And there are 2 duties which I wanted to do right now. So hopefully most of you have already downloaded and registered for the GitHub page and the GitHub Copilot. If you haven't made this, please do it so during the lectures. If you're stuck with any of the installation of the Visual Studio or something that you can also start and download, you can do in 5-10 minutes during the lectures or even in the coffee breaks. If you get stuck with this, any of us can help you to do this, to prepare for the hands-on session, because then we wouldn't lose the time on that. Yeah, so I think that's all from my side. And I think we are 55, so maybe we can just jump to the main section, and let me introduce Márton Makrai, who is a language scientist, if I'm doing well, and he's from the TTK, and he will introduce us to the secrets of large language models. And I really appreciate that he could, oops, what is this? He could manage to come with us. So, Márton, stage is yours, and thank you very much.
Thank you for the introduction. Yes, so I'm Márton Makrai, computational linguist, and this day will be about language models. And I would like to tell you about the background where the ideas came from. So we will start with the idea itself. So what is language modeling, and some traditional methods. And so first of all, I would like to mention that this slide is based on some other work. Especially, I can recommend this book, which is a textbook on natural language processing, and Márton. You can find there everything, and actually I use some slides by other people as well to prepare mine, and I also use ChatGPT. I hope it won't be obvious, but it's good to know that it's also a good tool for creating presentations. So language modeling, and so language modeling is a task to tell how probable a sentence is, and why do we do that? So why is it important? Historically, it goes back to the Cold War, when people wanted to know what the enemy says. So that was the time of great enthusiasm around machine translation. People thought that it is doable. Another application is speech recognition. So if you hear something like "I saw a van," then it's much more probable that this is the correct transcript rather than this. So I saw a van. Yeah, and optical character recognition is probably the third main application, where you have to know how probable a sentence is. I wanted to show you a picture, but I'm not especially good at drawing, so I used a tool. Actually, I prompted ChatGPT to create an image, but this channel from my brain through ChatGPT to this image turned out to be a bit noisy. So I'm not sure that what this image is supposed to suggest. But if you have guesses, then just look for me in the coffee break, and I will be interested in your guesses. So the noisy channel. So the noisy channel model of machine translation assumes that everybody thinks in English, or English is the target language. But in some cases, there's this noisy channel between your brain and your mouth, and then these clear English thoughts become expressed as those strange Russian sentences. So the task is to backtrack what was meant. And yeah, this is a maximum probability actually. So what is the English string which is most probable given that the foreign language sentence was what it was? And what is the problem with this? So actually, this is the question: how we will model this conditional probability. First of all, we use the Bayes theorem, which turns the conditional probability in the other direction. Why is that good? On the one hand, we are looking for the English string which maximizes this probability, so we are not interested in the denominator, and this splits the problem to two terms. One of those expresses whether the two sentences have the same informational content, and the other one expresses whether the sentence is okay in English. Okay, so these are two models, translation and fluency. And here comes language modeling. So that's why we are interested in how probable a sequence on its own is. The other part, language translation proper, is also interesting, but not the topic of this day. So how do we know how probable a sequence is? We apply the chain rule, so we have to compute the probability of each word conditioned on the previous ones. Okay, but how do we know this conditional probability? So when we want to compute, we are given the prefix water is so sweet that so how probable is that the will be the next word? Then we count how many times. So we don't do that, but this is the first idea. So how many times you see water is so sweet that the in the corpus? How many times you see that without the in the corpus? That's the conditional probability. What's the problem with this? Do you know? So the problem is that you won't find this in the corpus. Actually, nowadays, so this is a presentation example. So maybe in contemporary corpus is a text collection. If I use a term that you don't understand, then just ask me. So now you may find, but back in the time this was too long. So you make the Markovian assumption, which in this very in this strongest or strictest case says that the conditional probability of the given that this was the context, the previous context, is the same as if we just took the last word as a context. This is oversimplification, of course. So there are different orders. So according to the order of the Markovian chain, there are different language models which are called the n-gram models. So if we assume that every word is independent, that's called a unigram language model. which will actually produce words independently, which does not make too much sense. These example sentences are trained on Shakespeare, and as we go from unigram to bigram, so bigram is the case when you condition on one word, and trigram is when so the denominator is 3 words, so there is 1 word conditioned on 2. And so on. It gets better from 1 to 3, and maybe you realize that at some point it becomes actual quotation, because then if you are looking for such long n-grams in the corpus, then there will be only 1 occurrence. So the sentence can continue only in one way. So that's not exactly what we wanted. So you have to choose the optimal n for n-gram modeling. Okay, so why am I speaking about this whole thing? One of the basic topics is pre-trained. Okay, now it's called pre-training, but let's say representation learning. So who knows what representation learning is? Nobody. Okay. So representation learning. Or I ask it otherwise, what's the difference between supervised and unsupervised learning? Everybody knows, or much, but many people know. Supervised learning is the kind of machine learning when you have cold data, when you have feedback, so you know what the output should be, and you train the model to produce that output. And unsupervised learning is when you don't have the requested output during training. Representation learning is just almost synonymous to unsupervised learning. It means that the model has to learn some representation of the data. That's what we can require it to do. And in the case of language, okay, so who knows what pre-training and fine-tuning is? Yeah, yes. So so this part is pre-training when you train on a large bunch of text in this case, to learn the representation, where you have so kind of semi-supervision. So we are not thinking of a specific task, but the task is general. So we want to learn something about words, just about language. That's pre-training. And fine-tuning will be the situation when we have a specific task in mind, opinion analysis, sentiment analysis, or machine translation, or something like that. Okay, so we wanted to know only what words mean, and probably it's, I guess most of you are from physics, so who are professionals of physics. Yeah. But I come from yeah, it's not surprising. I come from a linguistic background, or yes, let's say, and there it's more surprising that when language models know something which is not clearly linguistic. So, for example, that New York is more probable than New Apple. That's knowledge about that's word knowledge, so not just linguistics, but that's maybe not that strange that word knowledge sneaks already into n-gram language models, or this sequence, the sun rises in the east, so rises in the east on itself, which is a 4 gram, so very simple thing to model, is probably much more frequent than rises in the west, or thank you, please. Oh, sorry, please, thank you. These kind of simple successions already represent some higher level knowledge, but basically we are interested in word knowledge. Okay, in machine learning, it is very important to evaluate the models. How do you evaluate a language model? You take a corpus, so a bunch of sentences, text, and compute the probability of each sentence. And if your sentence has n words, then you take the nth root, which is basically the average probability of the words. And you also probably normally compute the reciprocal because which can be thought of as if every word was had uniform this probability. So if perplexity is 600, then it means that the model was so perplexed by this text as if there were 600 equiprobable words. So that is the intuition behind perplexity, which measures how good a language model is. The lower, the better. And I also mentioned that there is the problem that you don't find every n-gram in the corpus, even if n is small. So there are some so-called smoothing techniques which move some probability distribution, some probability mass from the n-grams that occur in the corpus to the ones that don't occur. The simplest one is add one smoothing, but we don't have to go into the details. And I'm good with time. Okay. Do you have questions now? Okay, you can. Yes.
If you talk about sentence, how do you define a sentence?
So the task of breaking a text to sentences, this is a traditional task. The simplest method is to split up at every full stop, which won't be perfect because that's used for the purposes. So actually, this is so in traditional NLP, not in neural language models, but in traditional NLP, this is a task on its own. Yeah.
So can you recognize a comma and conjunctions where
you don't have to pay attention to the inner structure of the sentence, but somehow you have to decide. So in classical NLP, whether a dot is at the end of a sentence or just an abbreviation or what. So it's basically.
So this is rule based.
It used to be rule based. It doesn't have to be rule based. Yeah, the sentence tokenization. Actually, I don't know when this before large language models. Rule based is not bad. So you can do it rule based. I'm not sure whether they did it also by machine learning, splitting the sentences. And now that we have large language models today have great windows, so you don't have to split up the sentence as a pre-processing step, but larger units can be fed to language models. Okay. Another question? Okay. Basically, we are speaking about language models, but I would like to introduce you to word models as well. So let's talk a bit about count-based so-called. I don't like this term, that's why I put it in quotations. But okay, they are called count-based models. Lexical semantics. We would like to model word meaning. What do words mean? That can be modeled by their relations. So there are synonyms, words that mean the same, or antonyms, words that mean the opposite. Connotation, which means that words tend to be used in some emotional context. Traditionally, you had to know what, and the linguists are still interested, what the lemma of a word is. So, for example, the lemma of mice is mouse. Again, crucial problem. in word modeling is ambiguity, disambiguation. Words can be polysemous or hypernemous, which means that I don't go into the details, but that they have more meaning. Yeah, so what is synonymy? Theoretically, you have words, and actually there are some examples when words mean exactly the same. This is not typical, but there are cases. There are things which are similar. Cat and dog are both animals. Relatedness, coffee and cup, we know that they are related. You can verbalize how they are related. That's not that important, but they are related. That can be measured. I mean, you can ask people to tell how related these words are, and that is correlated with occurrence frequencies. Not directly, but with the appropriate post-processing. This will be the topic of this section. And also there are words, so for example, buy, sell, and pay. These words describe the same situation, but the roles are played in different ways. So when A buys B from C, is the same that C sells B to A. These are called semantic frames and semantic roles. The connotation is important in this story because this is one of the roots of machine learning word representations. So effective meaning is so there is a connotation is the aspect of a word's meaning which is related to the emotions of the writer or the speaker. So for example, fake and copy mean the same thing, but fake is negative, copy is positive. These words are used in different contexts with different emotions. And on the one hand, this has applications on its own, sentiment analysis, stance detection, and so on. And what is more important, and there was an experiment already in the 50s where Osgood and his colleagues asked people questions like, is liberty soft or hard? You had a scale from 1 to 7, soft and hard, and put liberty on the scale. And people of different mother tongues were asked many questions of this kind, and they applied principal component analysis to the data. And do you know principal component analysis? Okay, not many people know it. So it turned out that words vary along 3 main dimensions. So the 3 dimensions describe much of the variation in words. Can you guess what those 3 dimensions are? So what is the first one? Okay, so the first one is good, bad. Second one is arousal, so how much emotion it causes. And the third one is dominance, whether the thing or how we speak about it is dominant or subordinate. Yes, so why is this interesting from machine learning aspect? This means that words can be represented with some accuracy in a 3-dimensional space. Yes, I already spoke about this. This is an overview. So first I will speak about shallow or static word embeddings. They are word models which take words as independent of context. So in training you have the context, of course, but when you use these word vectors, so vectors attached to words, then context is not taken into account. And there are the more modern alternatives, of course. GPT, which uses a causal language modeling objective, which means it predicts a word based on the left context, and BERT. With these 2 architectures appeared actually basically at the same time. BERT has the masked language modeling objective, which means that some words in a sentence are masked, so hidden, and the model has to guess or predict what word there was. Okay. So, but let's return to the large picture, vector semantics. One of the roots is this it's also called semantic differential, or the 3 dimensions of effective meaning that I already mentioned. And the other one comes from linguistics. This is the distributional hypothesis, which starts with the distribution of a word, how probably a word appears in each context. Of course, there are infinitely many contexts, but this is the probable distribution. And the hypothesis is that words that have several similar distribution have similar meaning and or syntactic functions. So meaning and syntactic properties mix actually. It can depend on the window. So when you compute the distribution, then you take some window around the word, which and how you take the window influences whether you get semantic or grammatical properties. But basically, you know a word by the distribution. And these two ideas met, and that is vector semantics. So when you represent a word by a point in a vector space, actually, that's vector semantics. And yeah, now the third time that I speak about supervised and unsupervised. In this situation, unsupervised pre-training means that you have text and the model has to predict the next word or the masked word. And that's the way you get your word model. And later the word model can be used to, can be fine-tuned for the specific task. Yes. I would like to speak about two kinds of word models. The more traditional ones are sparse and long vectors, and the more recent ones from the past decade are dense and shorter, with just a couple of hundred dimensions. I will speak about how cosine similarity. So cosine is used for measuring the similarity of words, and actually these word vectors have had their applications in many tasks, and they actually the contemporary models, so BERT and GPT, can be also thought this way, that every word is represented, and those representations, so every word is represented by vectors. In deep models, more vectors, so one in each layer, of course. But in this sense, so it's still true that many kind of tasks are solved by word vectors.
Sorry. When you say that multi-dimensional space, what is the typical
Yes,
number
so
of dimensions
in the
contemporary case?
Yes, still a couple of hundred dimensions. So in GPT or BERT, I think it's 512. Am I right?
10,000 in the newest versions.
10,000.
Oh, so yeah. So sorry, I'm a bit outdated.
3 years ago it was 700. So it's
Okay.
yes.
Sorry. So I would like to tell you about so how we represent words and word co-occurrence with matrices. So we start with there are more formulations. One of those is the co-occurrence matrix, whose rows, both rows and columns are words, and each cell tells how. So, for example, you have cherry and computer and so Cherry and computer appeared twice. So they appeared together in two contexts. As a concurrence matrix, there are alternative formulations in which, basically historically, the columns used to be documents, or so those are the two variants. Whether the columns, so the rows are terms in each case, and the columns can be words or documents. Yes, and then the row represents a word, of course. So these are row counts, and we see in this example that similar words, so for example, digital and information, are more similar to each other than they are to cherry and strawberry, and we see that they co-occur with high frequency with the same words. So both co-occur with computer and data, and none of them co-occurs too frequently with pi. That's concurrence. And it was originally applied to information retrieval. So the task was to find documents which are similar to a query. And these kind of vectors are very sparse. So it cannot be seen from this example, but actually most values are zeros. So only there are only a few non-zero values in the matrix, which can be so the cosine, which is used for comparing two vectors, could be computed fastly. Now I would like to tell you about two kind of weightings of the yes.
Sorry, you just finished.
Yes, there's two kind of weightings of the vectors for comparing them. Yes.
And what about the storage requirements of this huge matrix? Because you may list in the column all the words,
yes,
word roots of the language in the row and column, and then make the numbers in the table.
Yes.
You have 500,000 words. Then it's 25 times time.
So back in the time you didn't have so many words, but that was the limitation. Yes. So actually you had to cut the vocabulary at some point. So take the most frequent some words, and how many words you can take depends on the memory. Yeah. Here only on the memory, because if you have to do singular wave decomposition, that's a larger problem. So then you don't. That's a larger problem than just storing. But here basically it's just storage. Yes. So cosine. What is the cosine? Why do we like the cosine? So we will measure the similarity of two vectors by their cosine. I guess I don't have to over explain this. So I already told you that if a word occur with the same words with large probability or with large frequency, then they are similar, and that's exactly what cosine captures. And if they occur basically with different words, then the cosine will be low. And what was the problem? That frequent words, so the row cosine will favor long vectors, of course.
What was exactly the relation that co-occurrence that they are?
So the co-occurrence matrix tells that digital and computer appeared together in 1670 contexts. Context can be a window, so in so many windows, or it can be larger. In the extreme, it can be a document.
Or they are neighboring words.
Yeah, in some window. Yeah, yeah. That's more typical than whole document. Yeah. So if the larger the window, the more semantic the vectors. Smaller vectors are rather grammatical, and if they are symmetric, so windows on both sides, that's rather semantic. And if they are one directional, So just on the left or just on the right, that's rather grammatical. There is this kind of relation, or at least there used to be such a relation back in the time. I mean, with these kind of early count-based word models. Okay, I think it's so if it's not clear, just yeah.
So it's, this measure is always positive, right? So
Yes.
It's not a negative answer.
Yes.
They use this probability between 0 and 1.
Probability. So here we are using frequencies, and just I will tell you that we normalize the vectors, so not raw frequency, but we normalize the vectors to length of 1. So that's not not to be a probability, but their L2 norm will be 1. Yes, and actually it turns out, so these vectors are strictly non-negative, and even nowadays, so in neural networks, the vectors tend to be non-negative. You don't have reason for that, but it seems so. Yeah, or in some cases, the mathematical relations interpretation can be shown, which tells why the vectors are basically non-negative. And maybe it's true even in cases when there's no reason for that, or we cannot explain why.
This on construction is positive.
Here, yeah, here when these are counts, yeah.
I wonder if you allow the neural network to build a representation. It may take negative values as well.
So in practice, once again, I ask Notabara to correct me if I'm mistaken, but I think that in most cases, even neural network representations tend to be basically non-negative. So,
but it is restricted to
no, they are not restricted. Yeah. At one point, so I will speak about word-to-vec and positive pointwise mutual information, and those two are related mathematically. So that's a case where we know from mathematics why the neural vectors are non-negative. Yeah, so we normalize the vectors for length of 1 because we don't want frequent words to dominate the data. Yes. We have already talked about this. Okay. There are two specific, yes, now I'm a bit over time. So I think I skip the two specific weighting schemes. Why do we weight words? Because there's kind of paradoxical relation that rare words are more informative. So if I say, I don't know, for the name of a chemical, for example, then or oxygen, just simply, then there's more informative when if I then take, which is a very frequent word. So basically, less frequent words are more informative, but very frequent. So frequent co-occurrence is very informative, of course, if words co-occur frequently, but if words are frequent on their own, then that kind of co-occurrence is not that informative. That's why we are using some kind of weighting for the co-occurrence counts, and one of those is TF-IDF, and the other one is positive pointwise mutual information, which I think I skip. So this is a summary now that these will be long and dense vectors, sparse, long and sparse, and every cell is still interpretable. So even after the weighting, you can know that this is some kind of association between these two words. Yes. So now, of course, you want to hear about neural networks. So I will tell the basics. the ideas, the concepts, the intuitions. Who knows the perceptron, the elementary neural network? Maybe everybody. It's not the best pedagogy, but I ask: is there somebody who wants me to tell what the perceptron is? Okay, that's the point where we can save time. And there are deep networks. And so if you know the perceptron, then I guess you also know what the deep neural network is, where deeper and deeper layers capture more and more abstract and more relevant features of the data domain. In vision, it means that more and more abstract forms are recognized in each layer, and in language, it's supposed to be and it's somewhat true that the layers of neural networks already in BERT correspond to linguistic levels. So we start somewhere with morphemes and syntax and semantics and pragmatics. Pragmatics is what syntax is the relations in sentences, and pragmatics is what is meant, or what the sentence is used. Yes. So I guess I can go on this slide as well. Maybe it's no surprise for you. Sometimes people ask what does neuron stand for? What is the meaning of the neuron? But so individual neurons don't have interpretations. And there is this also this interesting question whether this is somewhat similar to what is there in the mind, because it was motivated to be similar, but actually it is not. You know that, for example, so deep neural networks have these kind of layers, but there are no such layers in the brain, or the brain is not organized in that way, at least. Okay, so I think I can go on. If something is not clear, then just ask me. And then who is familiar with the backpropagation of error? Okay, we will finish soon. Static word embeddings. So static word embeddings represent words. I already told this that they represent words in a couple of hundred of dimensions. And I just mentioned here some Hungarian corpora. Of course, the newest one, Web Corpus 2.0, is the most relevant, which is so large that if you use only parts of it, that's already enough. There were corpora even before. What is important here is representation sharing, so that we are using the same representation.
Just a question. So in Hungarian case, what was what you used for? So what literature you use for collecting these data?
Yes. So this one, the original web corpus is a web corpus, as the name says. The Hungarian national corpus, so Magyar Nemzeti Szövegtár, yeah. Actually, its version 2 is larger. And that's a curated corpus, so that contains books and different kinds of literature from so not just books, but so it is curated. Yeah.
So it's like what is available in the electronic library in Hungary. That is
something like that. Yeah.
National library stuff like.
Yeah. Yes.
This is, I think, this library, the web corpus, it's about 80 gigabytes. You can download it.
The new one, yes.
And I tried it myself, and I find a lot of issues. So if you have web pages,
the author will be here.
There are a lot of issues because you have web pages multiply, so you have a lot of text which is several times in.
Yes, deduplication is an
and then
issue.
you have 100 kind of times how to write streets like Arany János utca. So
what's the problem with Arany János utca? Sorry.
So you have sometimes the same meaning with accent, without accent.
No, but that's a corpus, so that's
Yes,
what people
but
write.
it's not the same as the spoken language because it's some kind of and you have a lot of rating because you have a lot of web pages who repeat themselves. So
Yes, the two problems are very
or
different
you
kind.
have even the link of the web page, which is also in the text.
Mhm. Yeah.
So
Yeah, so to mention
a lot of issues with that.
yeah. So the deduplication and non-standard orthography are very different kind of problems. So deduplication, so that the corpus shouldn't contain texts very many times. It can contain the jó napot kívánok, so the greetings, of course, there will be many times in the corpus, but it shouldn't contain the same web page many
but
times, actually.
It shouldn't reflect the marketing, which company makes a better marketing, and you have
That's
so
I think
it's
that
like because it then gives an odd rating, so it won't reflect.
that's a question of social sciences. So you can see that this page is a very professional news portal. This one is propaganda. That's the task of social sciences to decide. So that's not a machine learning question, I think. Deduplication is one, and so how Arany János is written. So in this case, the corpus is what people write. So what we find there, that's the text. So we don't normalize. We never normalize the corpus.
Okay.
Yeah.
Actually, I don't want to make it long, but does it help if you have wrong grammar in the system? So for the learning process, if not everything is super precise in linguistic.
So now with deep language models, I think that it helps. Yes.
So it's a kind of noise in the
because that's like a genre. So like there's the present tense and the past tense of the sentence. There's the normal writing and there's the writing without accents. So that makes the representation stronger now with deep models. Yes. Okay. So there are these different architectures which I mentioned at least. So I can't go into the details. I'm not sure I will. With Word2Vec, which has more variants, skipgram or continuous back of words. Glove is a variant which is more strongly related to the original co-occurrence matrix based formulation and computes the co-occurrence matrix as a whole. So the processing is slightly different, and there has been fast text, which implies subword modeling, which means that there are long words, there are compound words, unknown words, or rich morphology. So there are languages like Hungarian where words have many forms, and in those cases it's a good idea to break down the words. Yes, and I will have slides about that as well. Okay, so Word2Vec. Word2Vec simplifies the task of learning word representations in some sense. It trains a classifier to tell whether some word is probable in the presence of some other one. So the classifier is binary, but it uses probability in the modeling, so it's not discrete, of course. So this is I think it's worth repeating that it's self-supervision, so it uses the text, the words themselves in the corpus as a supervision signal for telling whether they are probable or not. The positive examples are taken from the corpus from some fixed size window, and negative samples are also generated by taking some random word according not exactly to the unigram distribution, so not the frequency of the word, but some, say, smooth frequency probability of the word. and a logistic regression classifier is trained to distinguish the two kind of pairs. So why is it simpler than language modeling proper or word modeling proper? Because it's just a binary task, and yeah. So when Word2Vec was popular, then it was told that this is neural networks, deep neural networks. Actually, it's a zero level, zero layer neural network. So it doesn't have hidden layer. It's a log bilinear model in the sense that the probability of so given a pair, the probability of that they are real positive ones is is the sigmoid of the dot product of their words of the vectors representing them. Here is the sigmoid function, and the probability of them being a negative example is computed simply by it's supposed to be 1 minus the probability of the positive one. What is interesting here already that you have two vectors for each word. So each word can be a context word, and the focus or locus. There are no words. There's no terminology. I will call this one the locus. So the context and the locus. So there are two kinds of vectors for each word. You can and when you apply the resulting word representation, then you can take the average of the two or just drop one of the two. And here there's a simplifying assumption that all context words are independent. Okay. So how are skipgram embeddings trained? Basically as neural networks. So there's a random initialization, and the training objective expresses that the positive examples need to have large cosine similarity, and negative examples need to have low cosine similarity. Negative sampling is important because otherwise you should use the softmax, which is difficult because there is that great sum in the denominator. In negative sampling, you take k random negative so random words as negative samples, which is and here is it shown with which distribution the negative words are taken. Which turn and this magic alpha is 0.75. This turns out to be useful in several settings. So it's kind of a sweet spot. This loss function is maximized with gradient descent, and the context window can depend on the task. So that has to be fine-tuned. Fine-tuned for the task. Here are the other two methods I mentioned. Fast text, which breaks. So where, of course, where is not a very long word, so it's just an example. But some end markers are added, and subwords are taken. And the whole word is represented as a sum of the vectors of the subwords, which solves many out-of-vocabulary problems. And now, so fast text has been available for, say, 157 languages. So many languages. Now it doesn't seem very surprising, but maybe fast text was the first model which was available for so many languages. So before that, multilinguality in machine learning meant that the model handles two languages or several or a couple of languages, but this massive multilinguality was the novelty of the fast text word embeddings. And GLAV, this is what I was already mentioned, that this is a variant of the skip model, which is more closely related to the concurrence matrix based methods TF-IDF and PPME, positive pointwise mutual information mathematically. Word embeddings have interesting properties on their own. It turns out that the difference between king and queen is basically the same as the difference between man and woman, which is emergent. So it was surprising that the representations have this property. This is related to what is called the componential analysis in semantics. So that male feature is an element of the female feature. The gender feature is an element of the meaning of these words. It's also called relational similarity, so that the differences are similar. So this kind of semantic arithmetic can be computed by simple vector algebra. So man is the woman, king is the queen. There are also morphological word morphological pairs. Walking, walked. Walking is to walked, as swimming is to swim. And already these simple models encoded word knowledge, like the relation between a capital and a country and a capital, Spain to Madrid as Italy to Rome. And word analogies provide so-called intrinsic evaluation for word embeddings. So you can evaluate. So basically, you are interested in a task. So you are doing this for purpose, and your final goal is to be good in the final task. But maybe it's cheaper to first test your word representations independently of the final task. And one method for that can be word analogies. Theoretically, this can be done with deep language models as well, but that's not the standard way. Okay, and now I turn to just actually I have much time. Sorry. Yeah. Do you have questions? Okay, then I just would like to mention some ideas of the deep language models. So basically, the later speakers will tell you more about this, but I would like to concentrate on the conceptual questions. So recurrence on the first hand. If you have the data of so when individual data points have different length in time, that's natural language when sentences have different lengths. But I think it's also natural in physics. The data have different length in time. Then it's standard to use, or this is the basic idea, to use a hidden state, which not only depends on the input, but at each time step, the hidden state depends on its own value in the previous time step. Yeah. And this picture here shows that when you do backpropagation with recurrent networks, then you treat it as if it was a normal web network this way, so by projecting it in time. probably you also have heard about LSTM and GRU. So this is the problem of whether a recurrent model needs to remember. So actually, in recurrent modeling, these more complex. Yeah, so these are individual neurons, but it turns out that it is difficult for a neuron to learn what to remember in each time step and what to forget. So individual neurons are replaced by the so-called the long short-term memory cell. So short-term memory comes from physics. People have short-term memories. If you hear a phone number now, this is not the typical, but if you want to write down a phone number, then you can remember it for a short time. The problem was that recurrent neural networks had very long, very short-term memories. So the goal was to make that short-term memory longer. That's the strange name, long short-term memory. And that's why neurons were replaced with a cell, which is actually, this is the structure is very sophisticated, but the intuition behind it is just to know what to forget and what to store. And so this is LSTM and this is GRU. So you can see from the picture that they are different, but basically the same. And in some situations,
más csinálunk.
they turn out to be so GRU is better. Yeah. It was in mentioned translation that it was shown that the gated recurrent unit, it's called the gated recurrent unit, is somewhat better than LSTM. Attention. So the idea of attention came originally. So the idea is that sorry, I didn't speak about encoders and decoders, and the later speakers will do so. So an encoder is a language model which encodes text in the hidden representations, and the decoder is one which generates text from the hidden representations or models the probability of some output sentence based on the hidden representation. And in this case, it turns out that the decoder's input, so the input of the decoder part, should be a weighted some weighting of the hidden of the inputs. So this is analogous to translation. So when think of a human translator who is generating this translation. So first they read the whole sentence, but then as they generate the translation, the targeted sentence, then they look at different parts of the input depending on what they are just generating. So, for example, and why is this useful? Because words can get in quite different order. So for example, slowed is in the middle of the English sentence, but then verlangsamt is at the very end of the German sentence. So that revolutionized machine translation already in the middle of the last decade, actually. And this idea was included in the transformer architecture, which you probably have heard about, so BERT and GPT, which appeared a couple of years later. And here, the self-attention means that words also kind of attend to each other. So, for example, here is an ambiguous sentence, the animal didn't cross the street because it was too tired or too wide. So depending on the semantics of the words, we know that if it was too tired, that has to be the animal, and if it was too wide, then it has to be the street. And you can read out from attention weights. So this is from actual models that a transformer model. So when a transformer model predicts, so it's in the encoder-decoder architecture, when the decoder is supposed to predict it, then it pays the most attention to animal in the case when it actually refers to the animal because it was tired, and the other way around when it in the other case. So this is this idea of self-attention. And another, so this is the computation. I think that the hands-on will tell you as much as you need, but I just want to make a comment on the terminology. So you will see that there are three matrices, and some people just say, or actually David Nemeskei, who will be here today, for the first time he said that they're just names, so forget about this, what Q, K, and V are. But nowadays, I think that it's useful to think of it as a reminiscence of memory networks, where memories had to be retrieved somehow. So I mean, now they work better, but there were experiments even before to retrieve some memory from a network, so that the query, there's a query and there are key value pairs, and so in the traditional setting, and this is somewhat analogous to that there is so that the word is a query which wants to get some values attached to some keys. Okay, I don't know how much that intuition helped, but I hope it helped some. Yeah, here I wrote a slide for encoder-decoder architecture. So originally, the encoder-decoder architecture is for situations where both the input and the output is text, so machine translation or summarization. Yes. Okay. Do you have a question? Okay. And here the crucial thing. So in encoder-decoder, the whole input sentence is summarized in a single vector, a fixed length vector, and the output is generated based on that hidden vector. Yes, and I also mentioned the masked language modeling. So indeed, deep language models. And so actually, BERT and GPT appeared around the same time, but BERT became popular earlier, as far as I remember. The training objective of BERT is masked language modeling. One of them. There's another one. Next sentence prediction. Okay, so masked language modeling is when some words are masked, and the model has to. This is used for pre-training the model. The model has to predict what word there was. Actually, next sentence prediction is the task when two sentences are given, and the model has to tell whether this is a real pair of consecutive sentences or not. This objective was debated, it was dropped, it was reintroduced, so not that important. But the masked language modeling was very important for bidirectional modeling. Sorry, it's very important. I forgot to mention this, that BERT is bidirectional. It takes information for both sides. Actually, two recurrent LSTMs are woven together, and but GPT is traditional in the sense that it's a real causal language model which takes information only from the left. Okay. Here is what I already told about bidirectional language models, and some limitations. I thought I won't have time for this, so I didn't go in the details. I guess you hear about it, or if you are interested, you can look for it. We have to be aware that as soon as machine learning systems make decisions, and the more intelligent they are, the more important the decisions are they make, of course, then the more influential. And because they are trained on rubbish, as you already saw, that people cannot even write Aranya Shutsa with the right accents. So and actually, there are social injustices encoded in language, and that's what is used for training the deep language models. So and actually, language is worse than reality. So you can know that. Women have lower salaries, and it's more difficult, or for example, for ethnic groups, it's more difficult to get a job. That's the reality, but texts are worse. So language is even more justiceless, or how to say, than reality. That's why language models can make the situation worse. So we have to pay attention. They compute, they consume much energy, which is bad for our environment. And maybe more technical, but also very important, that these models are somewhat unstable with respect to random initialization. So whenever you work with neural networks, then be aware that the results you get can hardly depend on the random initialization. Okay, I think that's I wanted to say. Do you have questions? Oh, many, yeah. I don't know who was first, maybe you. Yeah.
So what happened to BERT?
BERT is still used. And actually, there is a variant of BERT, Roberta, robustly trained BERT, which was trained for longer, and it was optimized in some respects. And I think that Roberta is you could say, a strong baseline. Who knows what the baseline is? Great. It's important to mention, Laurie, that when you have a smart system, or a system which is supposed to be smart, then you compare it to something which is simple. So back in the time, a baseline meant that you have something very simple, simple but good. I said it, nice. I don't know what is called in English. So that's a baseline, and Roberta can be a baseline in that sense now. You know that nowadays there's some other direction, because there is, sorry, I didn't mention zero-shot learning, when you just ask ask the system verbally to do this and this, and okay, then the system does. So that's another kind of baseline. It's also called baseline nowadays, but that's very other baseline in some very other sense, because that's very compute demanding and very hard to interpret. And you know that it depends on the wording of the request very much. So, but in the original sense of baseline, I think that Roberto is a good choice. And yes, and the three other questions.
Can these models detect irony?
Nowadays they can, yes. I mean, that's a good direction for research. So there is research on irony detection, because it's difficult, because irony is when there is mismatch, some kind of mismatch between this and that, but you have to find the contradicting aspects of the sentence or more sentences next to each other. Yeah, so it's difficult, but there is research on that. Yes.
Actually, I have two questions. One of them is about this long short-term memory.
Yes.
That when you say that this reserve some knowledge from the previous, I don't know, steps or something like that. Does it mean that it fixes some of the veins in the model for some time, or what do you mean by that? So what do you mean by memory?
No, so it doesn't fix it, but it's just another neural network where a single cell is a single neuron is replaced by this kind of cell. So and now maybe you don't see from that part, but so here is the previous value, I guess, which comes in, and then there are these gates. So these are weighted gates, of course, which control how much the value should be stored or overwritten. So it's weighted in a weighted way, not frozen.
Not frozen, but somehow okay. So somehow we can remember some.
Yes.
Can I have a comment on that? Because
Yes.
LSTMs have a really
Come here because we don't have a microphone, I think.
okay.
Or you can switch on.
I just wanted to say that LSTMs have a really nice interpretation of a memory cell, actually, of a computer science-based memory cell, because you have your storage, your drawer, you know, the good old drawer. And then the first gate basically controls, this is a GNU, but this one, so the first gate basically controls whether you multiply this cell state by 0 or 1. There is a soft transition between 0 or 1, but it's almost binary. It's a sigmoidal transition. Then the second one decides what to write between -1 and 1, and whether to write, because there are two gates here. So this is basically the write operation in a normal binary memory cell as well. And then you have the read gate, which is a binary read operation, whether to read that cell or not read that cell. And we do that for all the vector dimensions in the cell state. So basically the cell state is the one that stores this information, which is close to binary, but represented by float vectors, because it's a soft binary thing. And due to this softness, we can use gradient descent or backpropagation to update with the chain rule. Because if it was binary, then you would have to deal with Dirac deltas as derivatives, and then that would be a problem. So yes, sorry for interrupting. Just to yes.
One cell, but you have the length of the feature.
The dimensionality of the feature vector, yeah. And for each element of the sequence, so for the length of the sequence, you do this update, forget update read operations all the time. So that's how it stores in this C vector. And then we will see in the next lecture that the difference between these and transformers is that transformers can directly access all the C's. These are just recurrently updating a single C. So that's the difference, I guess. And sorry for interrupting. I didn't want to steal your show.
Yes, can you explain how to, I have three questions. First one, if I have a word in plural, and the usual, or I have accusative
Cases.
cases where the grammatical structure of the word changes from the context, how to recognize that is the same word, how is that represented in this?
Yes, so this appears in all the models I mentioned. So the earlier models treat the word as a whole. So the two forms of he and him, these two word forms will appear in somewhat similar situations and in somewhat different ones. So so we cannot interpret it directly, but somehow it turns out that already the old models, so the concurrence matrix based models learn that these similarities. So both that he is more similar to Joan than to computer or I don't know.
Yeah, but what I want is like to know bread or not table and tables, how it will be the same thing if it's in plural or
Yes, because
are they have the different embedding or do they will be they unified and it's one embedding
yes,
table?
yes. So the main point is here multidimensional representation, that words are placed in a multidimensional space, so they can be similar to each other among more dimensions, and a subspace of that large space can represent grammatical similarities, and the other one can represent semantic.
So table and tables are different points in the embedding.
Yes. So every word form is associated with a vector. Yes.
Okay.
Yes.
The second question, if there are several languages in the world, thousands, are they models which cannot be applied for the language? So the languages are so different that I cannot.
Yes. Yeah. So
Some structural differences in the model must account for.
Yes, so there is differences between languages. So, for example, it has changed a bit. Before deep language models, I would have said that Hungarian is different in the sense that you have to pay special attention that words have many forms. So in Hungarian, Turkish, Finnish, these are languages which use suffixes, many kinds of suffixes on the same word form, while other languages, for example, English have just a few forms for each word. Yeah, and there are some. So, for example, in Semitic languages, there is this when there are the consonants and the vowels which go in between, and there are the so-called polysynthetic languages, which are spoken in some regions of the world when the information so much information like a sentence is wrapped in a word, in the sense that there is a fixed order, so those are not words but part of the same word. So actually I don't know, for example, how well deep language models work for polysynthetic languages. So there still can be difficulty with some language types. Yes, so actually there are 6,000 languages in the sense that the last speaker hasn't already died. So it's very pessimistic, but that's the situation. So most of the words are dying. Most of the languages are dying. Now language models do well on 100 or 200 and maybe a couple of hundreds of languages, and yeah, there are some more which we don't know actually, because, for example, when a new GPT comes out, they don't say that it handles Hungarian. And then but you try and you find that it handles Hungarian perfectly. So we don't know actually.
Good, thanks.
Welcome.
So I still have another question. Maybe I misunderstood that, but you said that when you put a sentence, that every sentence is mapped to a fixed length of vector, or what? Maybe
this was only the decoder. Yes, so I said this only for the encoder-decoder architecture.
How you do that? The length of a sentence can be very different. So it's same.
I think that there's a recurrence. So the input is processed with the recurrence, with the recurrent units, and the hidden state depends on the last state of the recurrent units.
But how can you handle different lengths of this?
Yeah, so basically, the main idea to handle sequences of different length is this recurrence.
So you cut different pieces or no?
No.
Going into a loop.
Okay.
That's not the number of words for you.
That's the number first, okay.
Yes.
Okay.
Okay.
Very typical question which used to raise in this situation, that how can you distinguish if I give you a text which is written by me or another one which I use the ChatGPT, how can you make, is there any method to make distinguish between them, or?
Okay, it's yet another question, but maybe not about knows more, but I will tell.
I will ask again.
I will tell my answer. I think it's that generative language models now are so similar. Generated texts are so similar to human generated texts that the task is somewhat nonsense. For example, if I told you that some of these chairs were made in Germany and other were made in Austria, and then I even tell you that this and that were made in Germany and those in Australia, and then tell me where this one was made. Then you don't know. I think the task is something like this, but there is research on it, and there is also a direction called watermarking, which means that the text should be generated in that way that a specific algorithm recognize them as generated. But that's a rule which model can follow or not. What do you think? So can generated and real text be distinguished?
If the generator is good enough, then not. So this is the good old arms race problem. If you have a good generator, then you need a detector which is as good as the generator. And if the generator is as good as the human writer, who is another generator in this system, then it could be almost undetectable. Watermarking systems are good, but in order to watermark a generated text segment, you need to alter the word selection distributions of the model. And if you alter it, then you will kind of destroy the semantic content of the distribution. So the performance of the model will degrade if you apply a hard enough watermark. So you have some trade-off between the detectability of the watermark and sensibility of the generated text. And nowadays, the state-of-the-art techniques are usually.
Oh, sorry, come here.
This is my last sentence. So nowadays, these are detectable for around 25% change of the text, because you might change some parts of the text, of course. So if the words in the text or the tokens in the text remain the same for about 75% of the AI-generated text, then these should be detectable if watermarked. If not watermarked, or we do not know who and how watermarked it, then.
No, the question is coming, for example, if you read different literatures and different writers, in some cases you can recognize the specific of a certain writer. So I mean, if I would get, I mean, this maybe my students some of them are here, so we can make an experiment that you can send me some text, like 10 sentences, and I can figure out who wrote it just because of the style. But this is an over average style, the ChatGPT, so it contains everybody. So if you are unique, then you can be recognized as, I mean, you can distinguish the person from the machine. But this shouldn't work.
So usually
You can come here.
Okay.
Yeah.
I'm joining the controversial discussion. So usually, what is an important thing is that, and we will get there in the next lecture, that there will be some few shot and zero shot learning examples where these large models have the capability of adapting to a given pattern. If that given pattern is an email from me, then they will be quite well adapting to that email, that pattern of the email from me. So if configured right, language model nowadays can really easily reproduce someone's writing style. Of course, there will be some limitations, and maybe the language models we can access are not the highest grade language models because they are for mass production. But these models will or soon will be able to mimic the style of someone in a way that it will not be distinguishable if we have a large enough sample. And then the size of the large enough sample is the question here.
Are you talking about one text or about a conversation? Because
A conversation is just a text. It would burn us.
If you start a conversation with ChatGPT, then if you pose a question which is making no sense, you can see that it's not a person. So if in a dialogue.
Yeah, if you configure this ChatGPT instance with enough examples of how a real person handles these situations, then it will adapt to the correct answer. So, of course, there will be jailbreaking techniques and there will be, let's say, limitations on the edges. But in base cases, these will be pretty close to how someone would handle this situation in another room in an unseen situation. So I think watermarking will be our only reserve in the end. And then the question comes, how do we validate or authorize messages? So the channels and the platforms should be authenticated after a certain point, and whatever message goes through with my private key, then that should be a message that is authorized by me. So if someone steals my key, then that's a problem. But having a high complexity and just a let's say a specific style will not be a guarantee of the source, I guess, in the upcoming 10 years. So it will gradually change, of course. It will not happen by tomorrow. But these methods, I think, of channel-based or platform-based authentication will be on the rise again.
Do you have other questions? We have a couple of minutes.
So it's more of a comment than a question, but so all these questions we are circling around basically boil down to the question of whether intelligence can be mimicked, right? Because what you're asking is basically, can a person with perfect memory sell themselves as a person with very high IQ? Because they can just memorize like scientific texts and they can just spit it back accordingly, right?
Generalization is also important here. Yeah, memorization is not enough, but these models also learn some latent emergent representation, which is yeah.
Just to Woman asked about to recognize irony. So it's difficult because if I learn to recognize irony, then I mislearn to recognize irony because the irony is something which is new. So I cannot find. So either I define to learn what is irony, but then I don't learn what is a new irony. Because
do you mean that irony changes? So what changes with
or if I say a joke,
yes,
a joke is either something a story or some language joke, which is therefore it's an irony because I never met it before. So and if
so
irony?
Irony is when you mean quite the opposite. So for example, you cook a meal and it does actually it's wrong bad, but you say that I'm I'm a perfect cook, so you say the opposite of what is the truth, and that's a stylistic method or way to express what you want to say. Or you can say somebody that you're very clever, but actually you want to say that you are not that clever that you think you are. So that's that is irony. Is it what you mean?
No.
Yeah. So that's
It's a contradiction, because if I tell a joke to someone, then it has this kind of some kind of contradiction in this sentence, which is ironic. But if I teach the machine what is irony, then he doesn't understand the new irony, because, well,
Right.
So if you could train on an ironic text alone.
then you don't understand, because
Then
the irony is something which is something new which we cannot learn.
Yes, no, I think
So
I
it's how-
understand
how
what you
to
say. Yes,
manage
yes.
this
So there will be ironic sentences in the corpus, of course, but the proportion of ironic sentences should be natural, and yeah. So if the whole corpus is ironic, then of course the model won't learn anything. But the proportion of ironic sentences has to be normal.
Chris?
So I was just wondering if you think that neural, like these networks can be used to, if there are efficient ways to store information that can then be searched, like in comparison to traditional methods, which would be like storing in like a database, or even in like a book where you need, like if I want to access data out of something stored, like via like reading a book or accessing a database and performing like a normal search through it, be like reading through the book and looking through the appendix, like where I'm trying to find the information, or if I'm just like performing a search through a database, like using a search engine. Like, do you think that these are efficient enough to like replace that stuff on a small scale? So say like if I had some information I needed to record, maybe it's a language, how people speak a language, and then I record it by just storing it in a neural network, and then people access it that way instead of it ever being like input into a database. Or is it always trained from a database, I guess?
We'll talk about this in the next one.
Okay, then this is the best.
So just to foreshadow the doom of it, the largest search engines already work by utilizing BERT-like language models. So from 2020 or 22, all of the languages of Google started to falling back to BERT-based or neural network-based search engines, basically. It's not stored in the weights because these are for representation learning.
Mm-hmm.
So they are storing the representations that come out from the network. That's the idea.
So if you are interested in such topics, then stay tuned. We have a half an hour.
Thank you very much. So we have the company. Thank you very much for this excellent introduction.